Let's go through how to solve a colligative properties problem in which you're called upon to find the empirical formula and ultimately the molecular formula of an unknown solute that's producing a solution. The problem we're going to use is the first semester final practice problem that's on page 7. One of the things we're going to have to figure for this problem is what's the mass of 1 mole of the compound in order to determine the molecular weight. Molecular weight is measured in grams per mole. So there's two things we're going to have or information, the grams and the moles. Now we're given the grams of our solute, the 91.2 grams, so we need to determine the moles. Now we can get the moles by using the freezing point change of the solution compared to the pure solvent by using the freezing point depression equation. The equation that lets us use the change in freezing point for our solution compared to pure solvent is change in temperature freezing is the freezing point constant times the molality times I. Given that we have an unknown hydrocarbon, that would make this a non-electrolyte, so our I value is going to be equal to 1. We're given that benzene normally freezes at 5.50 degrees Celsius, and we find that our solution now freezes at 0.86 degrees Celsius. Taking the difference will give us our change in temperature for freezing point of the solution relative to pure solvent. We now have our change in temperature freezing of 4.64 degrees Celsius. We can use this in our equation to calculate the molality because we're also given the value of the freezing point constant, our Kf value. We can now set up and solve for the molality of our solution. Solving for m, we get that the molality of the solution is 0.910. Knowing our molality of 0.910 and that molality is equal to moles of solute per kilogram of solvent will allow us to solve for how many moles of solute we have in our solution because we're given in the problem information how many kilograms of solvent we have. However, to calculate our kilograms of solvent, we have to use the volume of the solvent we're provided, 500 milliliters, and the density of the solvent, 0.8765 grams per cubic centimeter. Now, one of the things is that 1 cubic centimeter is the same as 1 milliliter in volume measurement. Using the density, we can set up a proportion. From the density, we know we have 0.8765 grams of benzene per 1 milliliter. Our sample, though, is 500 milliliters of solvent. This will let us get how many grams of solvent we have, which we can convert to kilograms, and then put in for our kilograms of solvent to solve for the moles of solute present. Solving for X gives us 438.3 grams of benzene, which is 0.4383 kilograms of benzene, and benzene is our solvent. So we now know how many kilograms of solvent are present in our solution. We can use the kilograms of solvent now. We know our molality is 0.910. We have X moles of solute per 0.4383 kilograms of solvent. We can now solve for how many moles of solute are present in our solution. Solving for X gives us 0.400 moles of solute present in this solution. Here's what we now know. The given quantity of 91.2 grams of solute represents 0.400 moles of solute. This allows us now to set up a proportion. We now know that we have 91.2 grams of solute per 0.400 moles of solute, which will give us how many grams or X grams of solute that would be present in 1 mole of solute, and that would represent the molecular weight of our unknown solute hydrocarbon. Solving for X, we find that the molecular weight of our unknown hydrocarbon is 228 grams per mole. Our next step is to now use the percent mass that we're provided for our unknown hydrocarbon to find the empirical formula and use the empirical formula to determine the empirical mass of our unknown hydrocarbon. Now, even though we've been given 91.2 grams of our unknown hydrocarbon, Mathematically, our problem will be now easier if we just say we have a 100-gram sample. Makes our percent work much easier to do. The percent by mass will be the same whether the compound is 91.2 grams, 100 grams, or any mass. The percentages of carbon and hydrogen in the compound will remain the same. If we say we have a 100-gram sample, then what we can do is say of that sample, 94.74 grams are carbon, and 5.26 of that sample are grams of that sample are hydrogen based on the percentages were provided in the given information. Our next step is to take the grams we have in our sample and convert this to moles of carbon and also moles of hydrogen. Solving for x, we find we have 7.888 moles of carbon in our sample and 5.21 moles of hydrogen in the sample. At this point, our formula would now look like this: carbon with a subscript of 7.888, hydrogen with a subscript of 5.21. We now need to simplify this and get this into lowest whole numbers, which would be our empirical formula. To simplify, we divide by the smallest number, in this case 5.21. This reduces our formula to carbon 1.51, hydrogen 1. Multiplying this by 2, and we get carbon with a subscript of 3, hydrogen with a subscript of 2, and this is our empirical formula for our unknown hydrocarbon. To get the empirical mass, 3 times 12 plus 2 times 1, that gives us an empirical mass of 38 grams for this empirical formula. Earlier we'd found that our molecular weight was 228 grams. Now the molecular formula has to be some whole number multiple of the empirical formula. So if we take the molecular weight and divide by the empirical mass of 38 grams, that comes out to be 6, which indicates that the molecular formula will be 6 times the empirical formula, giving us our molecular formula of C18H12, and that would be the molecular formula of our unknown hydrocarbon in this problem.